Hi everyone and welcome to video number 2. We've just done the introduction to trigonometry and today we're going to be covering trigonometric equations. This is going to be a very interesting portion of trigonometry and it will help enhance your knowledge in trigonometry math as you prepare for your UNEB in A-level. Alright, let's get into today's video. Alright, so next, today we're going to be covering trigonometric equations and this is what we're going to be doing today. Now, most equations in algebra have a finite number of roots, which means you can actually have an equation like x plus 2 is equal to 3, which will always give you one answer of x. So that means that is finite because you only have one answer of x. Then you actually have examples of quadratic equations, which usually give you two different roots, two different values of x. Then when we also have cube roots of x, for example, we'll actually have like 3 different values of x. But then most equations, as we're saying, most equations in algebra have a finite number of roots. That means they can be counted. But it says, but in many cases, trigonometric equations have an unlimited number. For example, sine theta, which is equal to 0, if you want to actually find the value of theta, so there will be an infinite number of values of theta that can actually give you sine being equal to 0. So for example, we actually have all these being able to give you the value that, so the sine of each of these values here will actually be equal to 0, and this continues infinitely. And then that's actually what happens usually with trigonometry. So what happens is we'll actually have expressions and equations where we'll actually have to create and set a boundary of how far you can go, so that we actually don't have to write all the different roots that come up. So this will actually make more sense as we do different numbers. So usually the range of values required is stated for you, and results from a trigonometric equation are summarized by writing which ratios are in each positive quadrant. So this is going to make sense as we do numbers, I promise. So we're going to be drawing a diagram that I call a cast diagram. So the cast diagram is a diagram that actually has different quadrants. So one of the quadrants is a region where all are positive, and then we actually have this other second quadrant where only sine is positive. Then we actually have this the third quadrant where only tan is positive. Then we actually have this fourth quadrant where only cos is positive. So the reason I call it a cast diagram is because when you remember it as cast, it will actually allow you to remember it easily. So cast simply means that we actually have the C for cos, the A for all, the S for sine, and the T for tan. So we'll actually be moving in this direction. So this cast statement will actually help you to remember the diagram properly. Alright, so let's try some numbers. So actually I have an example here where we're saying sine theta is equal to 1 over 2. And so we're saying for values of theta from 0 degrees to 360 degrees. So that actually means in this example, we don't want negative values of theta. So here we actually are limited have values of theta from 0 to 360. So actually have sine theta being a half. So how do we solve this? So we know that when we actually take the sine to this other side, we can actually have theta as being sine inverse of a half. So when we do that and we put it in our calculator, we can actually see that the sine inverse of a half is 30. So what we do is we draw our cast diagram. So this is our cast diagram here. So this is the region. So this is the region where cos is positive, all are positive, sine is positive, and tan is positive. So in this example, we actually have a positive value of sine. So that means we're going to place, so the answer we get here, so we know that sine inverse of a half is 30. So the answer we get here, we're going to place that answer, which is 30, in the different regions where sine is positive. So sine is positive in this region where all are positive, and in this region where sine is positive. So we're going to have it in this region and in this region. And then how do we place the 30 onto the diagram? So the trick is to always start your measurements and calculations from the horizontal line. So we're going to be counting 30 from the horizontal upwards. Then we're also going to place that in this other region also where sine is positive from the horizontal upwards. And that's why we actually have it drawn like that. Okay, and then how do we get the different values of theta? So we actually have the first value, which we'll get from navigating from here to there, and then that's how we actually get the first value of theta, which is going to be equal to 30. So actually have 30 as the first value, and then we actually have the next one. So we move again from 0 up to where we have this. How do we get this the value from here to here? I think it's easier to do 180 minus 30, which is equal to 150, and then that's why we actually have the two values as being equal to 30 and 150. Now we could have continued and done another rotation onward. So we'll actually have a rotation like this going past 360, and then we would have gotten a value like 390, but because we've been told to not go past 360, it means we don't need to get that other value. And then since we've also been told not to have negative values, that means we can't do clockwise rotation, so we actually are limited to doing anti-clockwise rotations. So that's why our two answers shall be 30 and 150, and that's actually how we do this. So let's look at the second example. So we actually have this second example where we actually have sine theta as being equal to -1/2. Now pay attention to this negative sign because it means something. So for values of theta from 0 to 360, so again we are only going to be doing anti-clockwise rotation, so no clockwise rotations in this example, just like in the former example. So we know now what happens is this this negative is only important in the cast diagram. So what happens is, to get the value that we'll put in the cast diagram, let's just treat it as a positive here, and you know, sine inverse over half is 30. So the only other place where you show that this was a negative is in the cast diagram. So we're going to be placing the angle 30 now in regions where sine is negative. Remember that here in all sine is positive, and in sine, this region of sine is positive. So the only other regions where sine is negative is in the regions of tan and in the regions of cos. So that's why we place the 30 in these different regions. And as usual, start counting from the horizontal line as you draw your angle. So actually I have 30 from here to here. Then you also have 30 from this horizontal line to here. That's why we actually draw it like that. So how do we get our first values of theta? So this is what happens is we rotate like this. So we start from 0, and then we actually have it being like that. Since we don't have negative values in our boundaries here, so we're only limited to anti-clockwise rotation. So the first value we actually have is going to be equal to 180 plus 30, which is equal to 210. And then we actually can do another rotation. And then what do we have here? It's easier to get this value by doing 360 minus 30, which is equal to 330. So we actually have the values of theta being equal to 210 and 330. So we could have done another rotation, but that would be going beyond the boundary of 360, and that's why we actually stop right there. So I hope you can see the difference, that when you actually have a negative sign, that simply means that in the diagram, place the value you get here in regions where it's negative. That's if you have a negative value here. Then if this is a positive value, you actually place these angles in regions where that is positive. I hope that makes sense. All right, so let's move to the next one. So we actually have this. So we know that we can actually bring this to this side. So we actually have 2 sine squared theta is equal to sine theta. And then as usual, in this example, we're also limited to anti-clockwise rotations. So for values of theta from 0 to 360. So this is an example where we need to first simplify. Now there is a mistake some students do, is they actually reduce this, and some students would divide both sides by sine theta, but that would be wrong, because when you cancel out some values you'll actually lose some of the answers. So I encourage you to not do that in this case. So what happens is, it's better to bring this sine theta to this other side of the equal sign and then leave a 0 on the other side. So that's why we have 2 sine squared theta minus sine theta being equal to 0. And then we can actually factorize this by pulling out sine theta out of the brackets, and then we remain with 2 sine theta minus 1 is equal to 0. So we can actually see that we actually now have sine theta as being 0. Then we also have 2 sine theta minus 1 as being equal to 0. So actually I have 2 different values. Alright, so we're going to first deal with the sine theta is equal to 0. And then what happens is we can draw our cast diagram, and then oh, sorry about that. So we actually have our cast diagram right here. So what happens is when we have sine theta as being equal to 0, we know that sine inverse of 0 is equal to 0. Okay, so what that simply means is we can actually not draw anything, because the angle would actually be putting on this diagram is actually 0. So we actually have 0 on this side, so it's just going to be on that horizontal line because it's equal to 0. Then when we also, so this is one region where sine is positive in the all section. Then we also have the 0 here, so it's flat because even in this region the sine inverse of 0 is 0, so our angle is actually 0 degrees. So our first value is going to be 0 in our first rotation. Then in our second rotation we actually have this, which is equal to 180. And then what we can see is we can actually also move and have the third rotation, and then we'll actually have 360 degrees. So 360 degrees is acceptable because we actually have 360 as being inclusive right there. So we have 0. So we have 0, which is the very first one. Then we actually have 180, and then we actually have 360. And those are the different answers. So that's when we have sine theta being equal to 0. Now what about for this section? So for 2 sine theta minus 1 is equal to 0, we can actually see that we can actually take this negative 1 to the other side, then we'll have a positive 1. Then we'll actually have theta being equal to sine inverse over half. Then in our cast diagram, we can actually see that our angle here is 30, and then we place 30 in regions where sine is positive, which is this region and this region, in the region of all and the region of sine. And then we can actually set our first anti-clockwise rotation is, we will have 30. Then we also have this, which is equal to 180 minus 30, which is equal to 150. So we can't do any other rotation because of the limit of not going past 360. So actually have 0, a theta being equal to 30 and 150. And then as a conclusion, therefore the roots of the equation from 0 degrees to 360 degrees are 0 degrees, 30 degrees, 150 degrees, 180 degrees, and 360 degrees. So I've just chosen to arrange them from smallest to biggest for organization. So what happens is each of these values of theta, when we put them back into this main equation right here, each one will actually give us, each one will actually make sense when you actually place it here. So each one will work and make the whatever is this side be equal to whatever be that side. That's if you substitute for the values of theta. Alright, so that is pretty helpful. So let's move on to the next question. So now we have this unique example where now we actually have different limits. So we're being told solve the equation 3 sine squared theta plus sine theta is equal to 0 for values of theta from negative 180 to positive 180. So what this simply means is we will not go past positive 180, but also we've also introduced a clockwise rotation. So that means negative values are also accepted in this case. So how do we solve this? Let's first simplify this. So what to do is the first step is to pull out the sine theta, and then we actually have this right here. So actually have sine theta being equal to 0, and we also have this being equal to 0. So we actually have sine theta. So those are the two values that we actually have. So for sine theta being equal to 0, in our cast diagram, we can actually see that we actually have, since we have 0, it's the same thing again. So we actually place the 0. So actually have 0. So we're placing 0 because sine inverse of 0 is 0. So we have the angle 0 here. So the first angle is actually going to be 0. And then we have the second angle as being equal to 180. Now we cannot do another rotation because we've been told to not go past positive 180. So that's the maximum on the anti-clockwise rotation. But this example also introduces a clockwise rotation. So that means negative value is accepted. So we can actually also rotate in the negative direction. So we actually have this. So before we did that, the first value is also still 0, so that remains the same. And then we actually have negative 180. So we actually have 0, 180 and negative 180 as all being true for this example. And then if we move on to for 3 sine theta plus 1 is equal to 0, so we know that when we actually rearrange this, so when you take the 1 to this side, it becomes negative 1, so actually have negative a third. So in reality, we're looking at an example where the value of sine is negative. So sine inverse of a third gives us a value of 19.5. So we'll place that 19.5 in regions where sine is negative, and that is because we actually have negative a third. So in regions where sine is negative, that is in the region of tan and the region of cos. So that's why I place the 19.5 there. And then in this example, we can actually not do an anti-clockwise rotation, and that is because the first value is bigger than 180. So we do not consider the anti-clockwise rotation. So what we'll do is we only consider the the clockwise rotation. So the first value is negative 19.5, and then the second value will be equal to, we actually have 180. So what's 180 minus 19.5? So the value we actually get there, and then the negative, so we actually have negative 160.5 in the negative direction. So that's actually the answers. So actually have negative 19.5 degrees and negative 160.5 degrees. Remember that the reason the values are negative is because this is clockwise rotation. So the values you get from clockwise rotations are negative. So therefore the roots of the equation, alright, so for our conclusion, so therefore the roots of the equation from negative 180 to positive 180 are, we're going to start from the smallest value, which was negative 180, and then we actually have negative 160.5, then we have negative 19.5, 0 to 18. So those are the different answers that we get here. So I hope this makes sense. So this is the example where we actually have clockwise rotations involved. And then we now have a UNEB question as our number 5. So in UNEB 2005, number 6, we were asked, solve the equation 2 sine squared theta plus 3 cos theta is equal to 0 for values of theta from 0 to 360 degrees. So the solution is this. So what happens is we actually have this equation right here. Then actually remember that from alternate form of Pythagorean identity, we remember that cos squared theta plus sine squared theta is equal to 1, which simply means that the simplest thing to do here is to make sure that both values are alike. So we actually want to change this sine squared theta to actually have a cos value in it also. So this Pythagorean identity here will actually help us because we know that sine squared theta is equal to 1 minus cos squared theta. So we're going to substitute the value of, we're going to put 1 minus cos squared theta where we actually have the sine squared theta, and then therefore we'll have 2 into 1 minus cos squared theta plus 3 cos theta is equal to 0. So when you open the brackets there, that's the value that we actually get, and then we actually have this equation right there. So we've actually rearranged it to look like that. So we actually have a quadratic form of display. So we can actually let the cos theta to be equal to x, so it actually looks more like a quadratic equation. Then we actually have this. So you can use any method that you would know and are familiar with for solving quadratic equations, either it's bulldozer or using your calculator. So for me to speed up everything, I used a calculator, and then I got the values of x as being equal to 2 and x being equal to negative a half. So those are the two values of x that I got, which means that cos theta is either 2 or cos theta is either negative a half. So for cos theta is equal to 2, we can actually see that the cos inverse of 2 is actually not possible. So that is actually undefined. When we press that in our calculator, there is no such value. So we cannot consider the values of theta from this one. So we'll actually now have to consider the example where we have cos theta being equal to negative a half. Right, for cos theta is equal to negative a half, remember that the negative sign simply means that we'll actually place our angle in regions where cos is negative. So cos inverse of a half is 60. So we're going to be placing this angle of 60 in regions where cos is negative. And where is cos negative? Cos is negative in regions, cos is negative in the region of sine and in the region of tan. So our angle is going to be in this and this region. That's why we actually have the 60 being there. Remember now in this example we've been told that we've only been limited to anti-clockwise rotation, so negative values are not allowed, so there's no clockwise rotation. So what are our first values? So we actually have this, which is equal to 180 minus 40, which should be 180 minus 60, which is equal to 120. And then we actually have this other rotation, which is the same as 180 plus 60, which is the same as 240 degrees. So these become our two different values. So therefore the roots of the equation from 0 to 360 are 120 and 240. So that's as easy as it was. So that's how you actually solve this UNEB number. So moving on to UNEB 2000 question number 13a, we are being asked to solve the equation cot squared theta is equal to 5 cosec theta plus 1 for values of theta from 0 to 360. So in this example we're also limited to only anti-clockwise rotations, but with a boundary of moving from 0 to 360 degrees. So how do we solve this? We can actually see that from alternate form of Pythagorean identity, we can actually see that cot squared theta plus 1 is equal to cosec squared theta. Now to simplify this, we are going to convert this so that it actually looks alike to this. Now the reason we do that is because cot has a form where we can actually have the value cosec within. So from this identity that cot squared theta plus sine plus 1 is equal to cosec squared theta, we can actually see that cot squared theta is cosec squared theta minus 1, and then we can actually substitute that value in there. So therefore cosec squared theta minus 1 is equal to 5 bracket cosec theta plus 1. So what happens is when you open the brackets on the right hand side, we actually have 5 cosec theta plus 5. And then when you collect like terms, we actually have cosec squared theta minus 5 cosec theta. Then when you also bring the 5 onto the left hand side of the equal sign, we actually have negative 1 minus 5, which is negative 6. And then we can actually let x to be cosec theta. So it's that it looks more like a quadratic equation. As usual, you can use any method of your choice, either bulldozer method, or I prefer using a calc to speed up my process. And then you can actually have x as being equal to 6 and x being equal to negative 1. So those are two different values of x. So we can say that cosec theta is equal to 6 or cosec theta is equal to negative 1. But remember that cosec theta is the same as 1 over sine theta. So we actually have 1 over sine theta being equal to 6 and 1 over sine theta being equal to negative 1. So in inverse form, we can actually see that sine theta is equal to 1 over 6 or sine theta is equal to negative 1. So for sine theta is equal to 1 over 6, we know that sine inverse of 1 over 6 will give us a value 9.59, and then we're going to place the 9.59 in regions where sine is positive, and that is in this quadrant and in this quadrant. So our first rotation will actually have 9.59 as our first value. Then we have 180 minus 9.59 as our second value, and then our values of theta are 9.59 and 180 minus 9.59, which is equal to 170.41. And then for sine theta is equal to negative 1, we know that sine inverse of 1 is 90. Sine inverse of 1 is 90, and then we're going to place this in regions where sine is negative because of this negative sign. So sine is negative in the region of tan and in the region of cos. So we're going to place our 90 degrees here. So what happens is we actually have drawn 90 from here to here, and then we actually have 90 on this line. Then we also draw 90 from this side, and then we also have it ending up here. So we actually have one straight line right here. So this is 90 and this is 90. But remember, we are limited to anti-clockwise rotation. So what will happen is we move like this, and then our first value will actually be 270, and that will actually be our only value because we can't proceed from there. So we only have the value 270. So what happens is, therefore, the roots of the equation from 0 to 360 are 9.59, 170.41, and 270. Alright, so number 6. Solve the equation tan theta plus 2 cot theta is equal to 3 values of theta, negative 180 to positive 180. Now, again, in this example, we've been allowed to do some clockwise rotations because the negative values are allowed here, but we're not allowed to go past positive 180 and past negative 180. So this is how we solve it. We're going to first simplify this equation here. We know that cot theta is the same as 1 over tan theta. So that's actually going to be the first step. So when we get the LCM, we actually have the LCM of this being over 1. The LCM is tan theta. So tan theta divided by 1 is equal to tan theta times tan theta, which is equal to tan squared theta, plus we actually have tan theta divided by tan theta, which is equal to 1. 1 times 2 is 2. So that's why we have this. So we're going to cross multiply here. When you cross multiply, we actually have tan squared theta plus 2 is equal to 3 tan theta. Then we're going to bring the value on the right hand side to the left hand side and leave a 0 on the right hand side. Then we have this. So when we have it in this form, we can actually express this as a quadratic equation. So we can let x to be equal to tan theta. Then we actually have the quadratic equation in this form. So as usual, use any method you like. I prefer using a calc to speed up the process. Then I'll have x as being equal to 1 or x being equal to 2. So that means tan theta is either equal to 1 or tan theta is equal to 2. So for tan theta is equal to 1, we actually can see that tan inverse of 1 is 45. So that means I'll actually have 45 in regions where tan is positive. And where is tan positive? So this is cast. So tan is positive in this region and in this region. In the region where all are positive and the region where tan is positive. So I'll actually place the 45 here and here. So remember, we count starting from the horizontal. That's why I actually have the 45 here. Then here also we count starting from the horizontal. That's why you actually have the 45 going right there. So we actually are allowing both clockwise and anti-clockwise rotations. So for the anti-clockwise rotations, our first value is 45. Now we cannot do another anti-clockwise rotation because the next value is bigger than 180. So we cannot do any other anti-clockwise rotation. So next we are allowed to do some clockwise rotations because negative values are allowed. So our first value will be this. I can easily get this by doing 180 minus 45, which is equal to 135. And since it's a clockwise rotation, that means a negative 135. So our two answers are negative 135 and positive 45. Remember, negative 135 is a smaller value than 45. That's why I placed it first. I prefer arranging from largest to smallest, but that's actually how we get the values right here. So that's for tan theta is equal to 1. How about for tan theta is equal to 2? For tan theta is equal to 2, tan inverse of 2 gives us a value of 63.4. So we also place that angle of 63.4 in the regions where tan is positive, and that is this region and this region. So that's why we have it that way. So our first value is 63.4. This is moving anti-clockwise. So there is no more anti-clockwise to move because we are not allowed to go past 180. So next we actually have this in the clockwise rotations. So this value is the same as 180 minus 63.4. And then we actually have negative 116.6. We make it a negative because we get that value from a clockwise rotation, and then the other value is 63.4. So therefore the roots of the equation from negative 180 to positive 180 are negative 135, negative 116.6 degrees, 45 degrees, and 63.4. As easy as that. So next we're going to do a question from UNEB 2012, and this was question number 10a. So solve the equation 8 cos power 4x minus 10 cos squared x plus 3 is equal to 0 for 0 degrees to 180. So in this example, only clockwise rotation, and in this example, only anti-clockwise rotations are allowed, but the biggest value should be 180. So there is no clockwise rotation, it's only anti-clockwise, but also we don't go beyond 180 because 180 is the biggest value. So first we're going to simplify this value here. Now this example is unique because we actually have a power 4 here. So we'll actually have to simplify that first. So we know that this is the same as cos squared x to the power 2. So that's why we can simplify it this way, so that we actually have something that looks identical to that. So what happens is, in this example, because we don't want to do any long division, we can actually just convert this to look quadratic. So what happens is we make we're going to let x to be equal to cos squared x. So I'm going to make it m this time. So m is equal to cos squared x. I cannot use x because x is already a value that we are searching for, so I'll let it be m. So m is going to be representing the cos squared x. So I'll have 8m squared minus 10m plus 3 is equal to 0. So using bulldozer method, I can actually find m as being equal to a half, or m being equal to 3 over 4. Okay, so we actually have the first, so that means cos squared x is equal to a half, or cos squared x is equal to 3 over 4. So for cos squared x is equal to a half, we can actually see that when we actually root both sides, you can actually see that the 2 will cancel, and then we remain with the root on this side. And then because of rooting of squaring both sides by half, we can actually see that the square root will actually be a positive or a negative, because both positive values and negative values here, once squared, will actually give you the value on this other side. So it will actually be positive or negative root of 0.5. 0.5 representing the a half. Right, so we actually know that x is equal to cos inverse of this value on this side. Now this example is unique because we actually have a positive root 0.5 or a negative root 0.5. So we actually have to deal with both categories in context. So let's first deal with positive root 0.5. So we're going to first draw a cast diagram for a positive root 0.5. Now when it is positive, we'll consider regions where root 0.5 is positive. So the regions where cos is positive, and that is in this region and in this region. So we'll actually have the angles here. So what happens is cos inverse of root 0.5 is 45 degrees. So actually place the 45 here and here. So remember, we're not allowed to go beyond positive 180, and then there is also no clockwise rotations, only anti-clockwise rotations. So our first value is 45 degrees. Now we cannot continue because we're not allowed to go past 180, so we only get one answer as 45 degrees, because we're also not allowed to do any clockwise rotation, so this remains our only value. Alright, so next we can actually go for the negative. So for the category where we actually have the negative root 0.5, we're going to place the 45 degrees in the regions where cos is negative, and that is in the region of sine and in the region of tan. So that's why we actually have it like that. So our only anti-clockwise rotations are allowed, so this becomes our first value here, and then we're not allowed to do any clockwise rotations, so we only have the value 180 minus 45, which is equal to 135. So x is equal to 135 in this example. So for cos squared x is equal to 3 over 4, we know that this means that cos x, when we root both sides and find the square root on both sides, is equal to root of 0.75, which is either positive or negative. So cos inverse of root 0.75, so when you consider the category where we actually have that as a positive, we'll actually have a diagram, because cos inverse of root 0.75 is 30. So considering the positive, in regions where cos is positive, we'll actually have the 30 on this side and this side. So our first value is 30, and then we cannot proceed further, so I only have x as being equal to 30. And then when you consider the cos inverse where we have negative of root 0.75, so that means we're going to place the 30 in regions where cos is negative, that is this and this. and then we actually have that, and then our first value will be that, which is 180 minus 30, which is equal to 150. So x is equal to 150. So we cannot get more values because we're not allowed to do clockwise rotations, and then we can't go past positive 180. So those are the values you get. So therefore, the roots of the equation from 0 degrees to 180 are x is equal to 30, 45, 135, and 150. So that's it. So next, I encourage you to try out these trial questions. So this will be helpful for your practice. Feel free to do each one of them, and I believe that as you do them, you'll get better. Trigonometry. If this video really helped you, feel free to leave a like on the video, and feel free to leave a comment to tell me if it was really helpful to you. And then if you're new to this channel, I still remind you to subscribe, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. See you all in my next video.